This video is about the Isaac Physics Year 10 Masterclass session about component characteristics and electrical power. The current that can pass through an electrical component depends on a few things, and one of them is the potential difference. Now we can show that graphically on a graph of current versus potential difference, which is what you can see here. This part of the graph is for positive potential difference on the x-axis and positive current on the y-axis. And this part of the graph is for negative potential difference and negative current. There are three components that you will need to know about for your GCSE: fixed resistors, filament lamps, and diodes. And I'm going to show you the characteristics for those three components now. Here is a graph for the characteristics for two different fixed resistors. One of them represented by this red line here, and one of them represented by this blue line here. We can use graphs like these to calculate the resistance of the component. So let's take the red resistor. When there is 400 volts across that resistor, 6 amps is allowed to pass through it. The equation relating potential difference to current and resistance is V equals IR. If we want to compute the resistance, we can rearrange this equation. R equals V over I. I can then substitute the numbers. 400 volts divided by 6 amperes. And if we were to plug that calculation into our calculator, we would get 67 ohms to two significant figures. That was the calculation for this point here. But we can also do the calculation for this point here, for example. And if we take those numbers, we have 200 volts divided by 3 amperes. And if I plug that into my calculator, I get the same answer, 67 ohms to two significant figures. So when we have a straight line on our characteristic graph going through the origin, we know the resistance for any potential difference will be the same. The resistance doesn't depend on potential difference. We've got the same value of resistance, regardless of what values of potential difference we chose. That's an ohmic component. If I perform this calculation now on the blue resistor, on this point here, 200 volts and 1 ampere. 200 volts divided by 1 ampere is 200 ohms. So you can see that the blue resistor has a higher resistance than the red resistor. The gradient of the blue line is lower than the gradient of the red line. For graphs where we have a straight line passing through the origin, a lower gradient will indicate a higher resistance, and vice versa. Well, let's move on to filament lamps now. The characteristics for a filament lamp are not a straight line, they are a curve. That indicates that the resistance does change dependent on the voltage, the potential difference, that's across the component. Let's compare the resistance for two different potential differences, 200 volts and 300 volts. Let's start with the 200 volts. Remember, resistance is voltage divided by current. And when we put our numbers into the equation, we get 50 ohms. We'll do the same thing for the second point. And just for clarity, I'll make that second point blue. The numbers are now 300 volts and 5 amperes. That gives us a resistance of 60 ohms. And so you can see we have a higher resistance at higher potential differences. The higher the potential difference across the filament lamp, the more current will flow through it. And the more current flows through it, the hotter it will get. The hotter it gets, the higher its resistance becomes. So let's look at the last component, which is a diode. And you'll see the characteristics look very different. This graph's a bit of a simplification, and you may see a bit of a curve at the bottom here. But there's pretty much no current flowing through your diode when the voltage is below 0.7, 0.8, it varies, but let's say 0.7 volts. But then when you have a voltage greater than 0.7 volts, current can flow. And in fact, the resistance becomes very, very low indeed. This line is very steep, goes up to very high currents without needing to put very much more potential difference across the component. We can say that the resistance of the diode at any voltage below 0.7 volts is very, very high. And that's indicated by this very low gradient. And the resistance of the diode at voltages greater than 0.7 volts is very low. And you can see that because the gradient is very high. But importantly, the reciprocal of the gradient is not actually equal to the resistance, but the gradient can indicate to us whether the resistance is higher or lower. This part of the graph here has a lower resistance than this part. The gradient is higher. The second thing we're going to look at in this session is electrical power. Now, there are some equations for electrical power, and I'm going to quickly derive those now. A reminder, power in general is an amount of energy transferred divided by the time it takes to transfer that energy. Power is measured in watts, that's a capital W. Energy is measured in joules, that's a capital J. Time is measured in seconds, it's a lowercase s. So that equation is the general equation for power. We then have some definitions. Potential difference is defined as the amount of energy transferred per unit of charge which is transferring that energy. And current is defined as the rate of flow of charge, the amount of charge that is transferred divided by how long it takes to transfer it. The unit of charge is coulombs with a capital C, and the unit of potential difference is the volt, and the unit of current is the ampere, or the amp for short. That's a capital V and a capital A. Don't get the symbols for the units confused with the letters in the equations. So it's possible to combine these two equations, the definition of potential difference and the definition of current, in order to get an equation that is an amount of energy transferred divided by time, which is what our power is. And we do that by multiplying together those two quantities. Potential difference multiplied by current. Potential difference was equal to energy transferred divided by charge, and current was equal to charge transferred divided by time. And you can see that the charge will cancel, leaving energy divided by time, which was our definition of electrical power. So electrical power can be written as potential difference multiplied by current. But potential difference was equal to current multiplied by resistance as well. So if I substitute this equation for V, I get I times R. One of these I's is from this expression, multiplied by R, and the other I was there all along, and simplify this to I squared R. Alternatively, I can rearrange this expression, V equals IR, to I equals V over R. To substitute that in place of I can get V divided by R multiplied by V, which is this expression here, which simplifies to V squared over R. So we have three equations for electrical power depending on what quantities we know. If I know the current and the potential difference, I can use this first expression. Current multiplied by potential difference is electrical power. If I know the current and the resistance of a component, I can work out the power that is dissipated in that component by using I squared R. And if I know the potential difference across a component and its resistance, I can work out the power dissipated in that component by using V squared over R. So summarizing those equations all on one screen, hopefully this is helpful for you. Here are all the equations that we've looked at in this video, and here are what all those quantities mean. Good luck.